Good morning, everybody. So today we have an extra seminar, a speaker from Postdam, from Germany. He's Alexis Reboul-Salze. He's now a postdoc in Postdam, and he did his PhD in Saclay, Paris. And he's going to tell us about MHD in proto-neutron star for formation of fast rotating magnetars. So you have the floor.
Thank you. I'd like to thank everyone for being here and thank Daniele for organizing this seminar and this visit. So I will present you the work during my PhD, where I work on the formation of fast rotating magnetars with an instability, with an amazing instability, the magnetorotational instability. So this was done with my PhD supervisor, Jérôme Guillet, and some collaborators from his ERC MacBoss, Raphaël Reynaud and Matteo Bupli. So I will first give a bit of context and the motivation about magnetars and extreme supernovae. Then I will present in more details the conditions specific to proto-neutron star and neutron star and the instability that is in question here, the magnetorotational instability. And then I will present two different models, one which is more simplified and one with more physical ingredients to be a bit more realistic. So the main motivation is to explain the formation of magnetar. I think many people here knows probably more than me about magnetars. It represents 10 to 40% of neutron star bursts. They are observed in gamma rays called soft gamma repeaters of X-ray in X-ray, anomalous X-ray pulsars with pulsation. And from this pulsation, it's possible to time them and to measure the spin and the spin down, which gives a constraint on the dipolar magnetic field, thanks to this formula of the magnetic dipole due to the spin down. And this gives a magnetic field of 10 to the 14, 10 to the 15 Gauss, which is very strong. And there are also some hints of an even stronger internal magnetic field. But we want to understand how these objects form. For that, we need to understand the context of neutron star formation in core collapse supernovae. So at the end of the life of a massive star, then we have an onion layer with different elements and an ion core. When this ion core goes above Chandrasekhar mass, it starts to collapse and it forms inside a neutron star. All the gravitational energy would be transferred to the proto-neutron star in the middle, which will be very hot. And you have a rebound and a stunning of the shock. The hot proto-neutron star then will cool down due to neutrino emission. And those neutrinos will deposit parts of their energy into the surrounding material, into the shock, which will be revived and then leads to the explosion of, so that's the standard mechanism for core collapse supernova with an energy of 10 to the 51 Earth. And so my study for the amplification of the magnetic field will really be focused on the center, on the hot proto-neutron star during the core collapse. So you have standard core collapse supernova, but you also have some more extreme one. You can have hypernovae, which represent approximately 1% of all supernova, which has a kinetic energy which is 10 times higher than standard supernova. And you also have superluminous supernova, which has a luminosity which is 100 times higher than core collapse supernova, as you can see here on this plot. And we definitely need more statistics for this supernova observations, which would be very nice with the Peregrine Observatory. And to be able to explain this extra energy, so either kinetic or luminosity, we need another mechanism that the standard neutrino-driven mechanism for core collapse supernova. And for that, one of the central engine of this extreme explosion would be to have a millisecond magnetar, so to have both strong magnetic field and fast rotation. For example, here, this leads to the formation of jet with the magnetic field light that are inward, and that creates magnetic pressure that pushes the material outward and create a jet. And for superluminous supernova, the magnetar emission can be injected into the ejecta, which leads to some late time energy injection and leads to those curve in proportional to T to the -2 for the luminosity. And the range of parameter for this kind of modelization, as you can see on the plot as well, requires a dipole field of 10 to the 14, 10 to the 15 Gauss, and a rotation around 1 to 10 milliseconds. So this is one central engine that could explain those extreme explosions. Can also, the same central engine could also be the case for binary neutron star merger. So in the case where you have a long-lived remnant, if you have like low mass binaries, or depending on the equation of state, you can have a remnant after the merger that survive for 100 milliseconds or 1 second or even longer, where you have also amplification of a magnetic field, and that could lead to the formation of a magnetar. And it could be the central engine also for short GRBs and launching the jet in a similar mechanism as the one for hypernovae. And so the magnetic fields of magnetar can also power some other objects, like more recently fast radio burst. So this is some short burst observation in the radio bands, in the radio band that has millisecond duration and an extragalactic origin. And in 2020, there was an FRB and an X-ray burst from the same plane for magnetar. Even it's a bit, so in this case, it's a bit lower in energy compared to FRB, but it seems to indicate that magnetars can produce FRBs. So in a short summary for the motivation, why do we want fast rotation and strong magnetic field? It's to explain the extreme explosion. And this is like typical the range of parameter that we want. Other model also exist and also can explain, can give similar observation. And this is why we need more constraint on the models and some better modeling. And in particular, one question is, how do we obtain such parameter for both the dipole and the fast rotation? How do we form so fast rotating magnetars? So different scenarios to understand how to amplify the magnetic field, how to form magnetar. The simplest one is to consider that we have a very magnetized star. We have some observations. Some stars have a very high surface field. And if we think that we have flux conservation during the collapse, we obtain a magnetic field like a magnetar strength. But the thing that we should be a bit more careful, because what matters is not the magnetic field at the surface of the massive star, but the one inside in the iron core. And it's not as clear as if we can have a field of 10 to the 10, 10 to the 11 Gauss in the iron core of massive star. Some study shows it, like for example, when we have star mergers, that can happen. But since they are very magnetized, this star spins slowly, so it cannot explain the formation of have both fast rotation and strong magnetic field. And this is why we need to have amplification inside the proto-neutron star due to the fast rotation to get both at the same time. There is another scenario which is slow rotating and more recent, which is the Taylor-Schroot dynamo. I will come to this a bit later, where the proto-neutron star is spin up by the fallback during the core collapse supernova. And you can have the Taylor instability kicking in and forming a dynamo. Yes, and when you have fast rotation, you have two other mechanisms to have the amplification of the magnetic field. So convective dynamo, which is very similar to planetary and stellar dynamos, which explains why we are so interested in MHD in general, and also the magnetorotational instability that can be applied both to supernova and neutron star merger, and that has long been studied in accretion disk. But to give an idea where those two mechanisms plays a role in the proto-neutron star, this is a typical proto-neutron star 0.2 seconds after the bounce during the core collapse. And you have an inner region which will be in solid body rotation and stable to the convection. So it's fully stable. Then you have a layer which will be convectively unstable where the convective dynamo can happen. And then you have decreasing differential rotation, which will be unstable to the MR. So quickly, I would like to go back on this new scenario to form a magnetar to fall back and the terrestrial dynamo. The idea of this scenario would be that so we have a proto-neutron star and we have matter that falls back onto the central object and that spins up the central object, which means we have positive differential rotation. Then the initial magnetic field would be amplified by the shearing. So from the initial dipole, which will create toroidal field. When this toroidal field is strong enough, then the Taylor instability will also called kink instability will destabilize this toroidal field like a pile of plates. And when this small scale field is strong enough, it can have some nonlinearity that will generate back some radial magnetic field, and you have a loop like this that can reach a saturated state. And depending on the accreted mass, as you can see here, you can form quite a strong magnetic field. So this is a one-zone model where we just have simplified equation and no radial profile or anything, just one zone. And as you can see, for larger accreted mass, you can reach 10 to the 16 even for the toroidal field and the range of Magnetar, the gray zone here. And this is also explored in simulation. If you want to talk more about that, please come see me later. We can discuss a bit more. We'll also just mention the convective dynamo. When you have fast rotation, so here it's a period of 2.1 milliseconds, and you have different phases. So you have first a kinematic growth where the magnetic field is not strong enough to affect the velocity of the convection to the convective cells. And you can see here on the plot, you have this like vertical convective cells developing inside the simulation and some magnetic field lines. But you can also reach a second stage. So this is the stage of the first plateau. You can also reach an even stronger where you're above equipartition of energy. So you have more magnetic energy than kinetic energy and reach a toroidal magnetic field of 10 to the 16. And you can see that the convective cells are really broken by the magnetic field lines. And in this simulation, we also reach the dipole, which is here in orange. It's possible to reach 10 to the 15 Gauss. So really for a magnetar. So the simulation has been done by Raphael Reynaud. And for this, now I would like to focus more on the scenario that I'm interested in, the magnetorotational instability.
Alexis,
yeah.
One question. In this dipole component you show, is the one at the surface or is the average in the volume?
The average in the volume.
The one at the surface is the same order of magnitude or is lower?
Actually, I'm not sure. I would expect it to be the same order of magnitude. But yeah, that would depend on boundary condition after. Yeah, but this is not the same. Yeah, it should be zero at the surface because actually it's perfect conductor boundary condition. So there is no dipole field at the boundary because of that.
Okay. Yes.
So yeah, that's why you usually look more into the average inside the domain than the surface.
Okay.
Okay, so that's for other scenarios of forming fast rotating magnetar. Now I would like to focus more on the magnetorotational instability. So let's get back to some properties of the magnetorotational instability in a simple case. So if you have decreasing differential rotation and a magnetic field line here that connect two elements, if you move slightly the two elements, the magnetic field will act as a spring between the two elements and give the angular momentum from the outer element, so this element, to the inner one. the opposite. Sorry, the inner one will, since it will come inside the differential rotation, then by conservation of angular momentum, it will spin up and transfer this spin up to the magnetic field, to the exterior element, which will then spin faster than surrounding element and will then be pushed outside and will lead to an instability. So it drives the instability that we call the magnetorotational instability. So the main criterion to have this instability is to have decreasing differential rotation. It also have a fast growth rate. This comes from linear analysis, so proportional to the rotation rate. So this is why we need to have fast rotation to be able to amplify the magnetic field during the time of a core collapse quite fast. But the wavelength of this instability is proportional to the magnetic field, which means that it has a short wavelength if you have a weak magnetic field, which would make it very difficult to have amplification over many different scales, because numerically you need to be able to resolve these wavelengths. And this is why this instability has long been studied in local model. So where we take only a box, either of the proto-neutron star or the accretion disk, and to be able to resolve these wavelengths quite clearly. So this is, then you have many conditions specific to neutron star. You can have entropy and compositional gradient with the electrical fraction, so buoyancy. So this is an example of stable stratification in some of these sharing boxes, where you see that when you increase the buoyancy parameter, it reduces the turbulence compared when you have like a convectively unstable region. So it can dampen the turbulence in the equatorial plane. You also have some neutrinos are very important for proto-neutron star, and also have a spherical geometry that we cannot have in these local models. So to see that we are unstable to the MRI, we can take a look at some rotation profile in a core collapse simulation, and also for binary neutron star merger, and both are quite similar. We usually have almost solid body rotation before 10 kilometers of the proto-neutron star, and then we have decreasing differential rotation, which will be the zone unstable to the MRI. For the impact of neutrinos, it really depends on the scale you're considering. If you are at larger scale than the neutrino mean free path, then you can approximate this effect as viscosity. And if you are at lower scale than the neutrino mean free path, then it can act as a neutrino drag on the matter. And so for the wavelength of the MRI that you see here, it's usually higher than this mean free path. This means that there is a strong viscosity applying to the instability, 10 to the 10, 10 to the 13 centimeters square per second. And this has been studied, the impact of viscosity and resistivity is something very important for the magnetorotational instability, and especially the ratio, which is called the magnetic Prandtl number. So the conditions for proto-neutron star would be a value of 10 to the 13. And it has been shown in previous studies in accretion disk that if you increase the number, you can of this ratio, the magnetic Prandtl number, you can have dynamo much easily for lower Reynolds number. So it makes the magnetic field gets stronger. Here it's the angular momentum transport. You can see that with PM, it goes higher when you increase PM. And it raises the question, since this is not a regime that we can obtain in numerical simulation, can we obtain some kind of plateau, imagine far 100, 200 PM, and can stop increasing the magnetic energy? So that's mainly for numeric. For local models, then there has been spherical and global model. The first model by Philippe Mosta, 2015, where he simulated a quarter of supernova, and it was one of the first time that the resolution was high enough to resolve the MRI in such a global simulation. But this simulation already starts with an initial dipole field. So we cannot be sure that the dipole field that is found in the simulation Is it from initial condition or is it from the MRI? And it also have very high computational cost because it has a lot of physics. And lastly, since there is only a quarter, some modes are not accessible in this simulation. For example, the equatorial dipole, which could be important, cannot be simulated for this. So it's an improvement, but it cannot answer all questions. And this is why we developed a simplified global model. So the first one, the idea was to be the simplest possible, just have the key physical ingredients. So this is why we use the incompressible approximation. So we filter the sound waves because usually the sound speed in neutron star and proton star is very high. So we can quite safely filter those sound waves, which make it less numerically expensive. We also assume that the neutrinos are in the diffusive regime because then we just have a strong viscosity. And to be able to study really a quasi-stationary state of the turbulence, we forced the differential rotation at the outer layer. So this was the idea for the first model, where we also chose like standard density for proto-neutron star and a radius of 25 kilometers. And therefore, we solved the incompressible MHD equation. So you have the Navier-Stokes equation, the different term, pressure, the caracterised force, viscosity, and the Lorentz force, and the induction equation. So this is adimensionalized. This is why we have three parameters that arise with this equation. So the Ekman number, which is the ratio of the viscosity divided by the caracterised force. So typically for neutron star, it's low but reachable in simulation. And the magnetic quantum number, which, as you can see, for numerical reason, we cannot reach such the realistic number 10 to the 13. We have to reach something, so we choose to be at 16. This way, it's closer to the regime that we want, but not quite there yet. So to solve this equation, we use a code from the stellar and planetary dynamo community. I think some people here knows it. So it's a pseudo-spectral code, which leads to a low numerical difficulty, so it's very nice. It can use its different soundproof approximation, not only the incompressible, but also Boussinesq and anelastic. I will come back to that a bit later. And we also have something very important, is explicit diffusivities. So we can fix physical values for the viscosity and resistivity, and it's especially its ratio. And yeah, it uses spherical harmonics and Chebyshev polynomials, and it's highly optimized. So I use this initial condition for the initial condition of this simulation. So it's a profile inspired, differential rotation profile inspired by those in collapse supernova, where you see that you have a solid body rotation until approximately 10 kilometers, and then decreasing power law with here a value of 1.25. And what's really important for the magnetic field is that we start from a strong magnetic field to be able to resolve the MRI, because if it's too low, then the wavelengths would be too small. But we initialize only small scale. So there is no dipole here. There is no large scale. It's really only these small patches, because we want to see from the local amplification, how do we get the global structure of the magnetic field? And with this initial condition, I run the simulation, and this is typically a snapshot of the magnetic field amplitude inside the simulation. You can see, so the small scale turbulence that look a lot what you can find in shearing boxes on this meridional slice, and you can see the winding and the shearing of magnetic field, so larger patches in the equatorial plane. But it seems that here we don't see any large scale arising, so we'll have to look into a bit more details. And we can also take a look at the quasi-stationary state, so the time evolution. And you can see that quite fast you reach a stage where the energy doesn't move much. And we can make time averages and statistical studies for the quantities like the toroidal magnetic energy, which is higher than colloidal magnetic energy. it's a ratio that is similar to what can be found, has been found for this instability in previous studies. So this gives the turbulent field, but we can also take a look at the dipole because the observation constrains mostly the dipole. And as you can see here, the dipole is much lower. It's around 20 times lower in terms of magnetic field strength, so 2 orders of magnitude lower in terms of energy. But we still generate a dipole. And what's also interesting is that the angle, the tilt angle, so the angle between the spin axis and the magnetic axis of this dipole seems to be mostly equatorial, so around 110 degrees or 70, 80 degrees. While for simulation of core collapse, it was often before axial dipole that was used. So this really shows that we can have different geometry arising from this instability. And this is the result for one simulation, but we wanted to check what was the impact of initial magnetic field condition and boundary condition. So we...
You started with 0 dipole.
Yes, I start with 0 dipole.
This component is just what you have produced
Exactly.
by MRI.
Yes.
Did you try, maybe you're going to say, but did you try, I mean, the 0 dipole, we agreed that fossil disk can be, that is not the only, but that there is a dipole of some kind from the start, there will be.
Yes.
I don't know how much of this trend. So did you try to put a very tiny weak dipole and the MRI and see?
So then you will not see the difference because the small scale turbulence will be much stronger and then generates the stronger dipole. What you can do in sharing boxes is that start from this weak dipole, and then you can have an amplification towards like 10 to the 14, 10 to the 15. This is why I start from this small scale, because local simulation has shown that we can amplify the magnetic field, even from a weak dipole to this kind of values, but only on small scale. So here it makes the... And what was very nice is that it didn't depend on any boundary condition or initial condition. You can see it's all in the same range, around between 1.9 and 2.6, 10 to the 15 Gauss for the average magnetic field. And similar for the dipole, there is a nice linear relationship where the dipole represents 5% of the magnetic field strength. So this was a nice result. And since this was the first global model in spherical, we wanted to compare more precisely towards a local model. So Jérôme Guillet made some simulation with the code Snoopy. This is like the size of the box that we chose to be able to compare well. You can see the comparison of the simulation domain. We compare 2 things. We compare where do we obtain dynamos if we change the magnetic Prandtl number. So if we increase resistivity, then in some cases we don't have any more dynamos, or just some transient one that decreases. But if we have a high enough number, then we can match the same dynamo threshold for both the global simulation and the local simulation. So we choose this parameter that were matching well. And we compared the magnetic and kinetic spectra for the scales. And you can see that we obtain pretty similar results. So both are in a good agreement. And this good agreement and the low cost of local simulation allowed us to explore even higher magnetic Prandtl numbers. So here it was 16, but we went in a different. So transient, it means that you don't reach a quasi-stationary state. You have some turbulence for like 100 milliseconds, and then the turbulence just is dissipated by the viscosity and resistivity. So it's like no dynamo at all, but just something that lasts for 100 milliseconds or so.
So yeah, turbulence at the beginning, but it's
exactly.
But don't you keep adding like don't you keep forcing the differential rotation?
Yes, you keep forcing the differential rotation, but
so this means that viscosity and diffusivity change.
No, they don't change, but the dissipation is stronger than what the Gauss rate of the instability, basically.
the dissipation of
the perturbated field and all the small,
turbulent dissipation.
yeah, which is linked to the viscous scale and resistive scale. So that's why we have only some transients. So yeah, the good agreement made us think to go towards higher magnetic Prandtl number, and this is the result. So you can see that 16 is here, and we went all the way to 200 in local boxes, and very nicely we find a plateau starting from 100. First, we have a linear relationship, so the magnetic energy scales linearly with the magnetic Prandtl number until it saturates, and therefore we have a factor of like 7 between PM equals 16 for my global simulation and what could be reached in local simulation. You can see that the velocity doesn't change much between the two, because we are only, to increase the magnetic Prandtl number, we're decreasing resistivity, and that's why the magnetic field scales decreases, as you can see here, compared to PM equals 16. But we were worried that maybe then this factor could not be applied to the dipole. But when we check the larger scale of inside the simulation, they are also amplified in a similar relationship as the average magnetic energy. So this really shows that we can think to extrapolate the value of the magnetic field from global simulation and increase it like this plateau, so a factor of approximately 7. This gives reasonable lower limits. And this result are also been found by a different independent study by Lauren Held, which is also in Postdam, which he tried for different parameters, different shear rate, different viscous and viscosity and resistivity parameter. And he also found a similar plateau here around 200. So the incompressible model is very nice. It's very, very cheap to simulate, but it's not very realistic. It's too simplified for proto-neutron star. So we need to add new ingredient, density and entropy stratification. And this, in equation, this has been shown that when you add a vertical density stratification, some mean field epochs effects, so this is an axisymmetric average, give rise to the butterfly, what we call butterfly diagram. So you have reversal of polarity during time and rising element of flux here. So this shows that it should be a very important element. And we applied 1D model. So we take data from 1D core collapse supernova simulation from the Gaussian group. And we simulate, so this is the tree zone I was telling you about. So the stable zone to the MRI, then you have the convective zone and the stably stratified but unstable to the MRI. And because it's difficult to have both zones at the same time, we focus only on the stably stratified region where it's stable to the convection. So it's really close to the surface of the proto-neutron star, so for density 10 to the 11th gram per centimeter cube. So, and the ratio between the inner boundary and the outer one of density is approximately 70. So this is where we use the analytic approximation, which allows us to use this profile as a static background, so it doesn't evolve in time. We just take all these quantities and put in the simulation and then evolve the perturbation. And we use otherwise similar hypothesis as before. For the neutrinos, we use diffusive, still the diffusive regime with constant diffusivities. And same as before, we force the differential rotation at the outer boundary. You can see here some typical values inside the simulation, viscosity. We kept almost the same values for both number for the viscosity and also for the ratio of viscosity over resistivity to be able to compare the two models more easily. And this is the equation that we solved. So what changed compared to before? We have a new term, the buoyancy term here, that wasn't there in the incompressible model. And then we have all the term that comes from the profile in the thermodynamics. So you have the density profile, temperature profile, that is important for this simulation, and it gives us two new parameters. So the ratio of viscosity over the thermal diffusivity, and also like the Bund-Weisser frequency, which can be linked to the Rayleigh number here. So for this Bund-Weisser frequency, what matters is the ratio over the angular frequency, and you can see here that it's quite high. So we can expect that it impacts the turbulence, at least in the equatorial plane. And for the initial magnetic field, it's also small scale as before, no large scale, no dipole. It's just stronger on the inside because we wanted to have a constant Alven wavelengths to have the same MRI wavelengths into the domain and be sure that we resolve everything. So from this initial condition, we'll let the system evolve. And you can see the magnetic field lines here, where you have, as before, in this plane, the winding and the shearing of the magnetic field that leads to the structure. And you also have some small loops, which will be interesting as well. So that's the poloidal turbulence. And this turbulence, surprisingly, we were not expecting that, is very localized. So there is no turbulence in the equatorial plane. It's also focused into the lower density region, but that's mainly an artifact because we are forcing the differential rotation on the outer layer, which means that it's very efficient for low density, but it's not as efficient for higher density, which means we don't have a forcing strong enough to have turbulence in this region. So this is a snapshot. We can take a look at the evolution of energy, and we find similar ratio for the magnetic toroidal energy and the magnetic poloidal energy as before. What is a new behavior is we have this kind of oscillation, strong oscillation that were not in the previous incompressible model, and it looked like mean-field dynamo that is found. So the butterfly diagram, and that is found in stellar physics. So we can interpret the simulation in this theory. So what the principle is that we separate the magnetic field and the velocity field in two quantities, an average one and a small scale one. And then the induction equation for this mean magnetic field, as written here, is almost similar as the previous like the standard induction equation, but it has a term, an average term from the small scale. And you can, this is the amplification that comes from the non-linearity of the small scale. So the U cos B, which we call the electromotive force. And to have a dynamo loop, usually in this theory, you have two main effects, which is the omega effect and the alpha effect. So the omega effect is the shearing of the poloidal magnetic field. So when you have differential rotation, you can see here, it generates some toroidal magnetic field. And then to close the model, what is usually done in mean-field theory is that the electromotive force is written with some coefficient proportional to the mean magnetic field or the derivative of the mean magnetic field. And this is typically the alpha effect, where when the electromotive force is proportional to the magnetic field, we can have a rising element here that will then spin due to some vortexes of the turbulence. And this, so this loop of magnetic field will create current parallel to the magnetic field lines, and then will regenerate some poloidal magnetic field. And then with these two effects, you can have a full dynamo loop. This generates the toroidal field, and from the toroidal field, the alpha effect generates back the poloidal field. Another effect that was studied for the MRI is the turbulent resistivity. You can have some non-diagonal element for some simulation that was found in this study, where some non-diagonal elements were able to generate the average field. So to see if we can analyze our simulation with this theory, we can take a look at visual correlation. So for the omega effect, it's quite simple. We see that the toroidal magnetic field is anti-correlated to the radial field. This is due that because we have decreasing differential rotation, this is why it's anti-correlated, and you really see those reversal of the magnetic field here in time. And for the alpha effect, we can also see that the electromotive force, the component from the small scale, is proportional to the mean field toroidal, the mean toroidal field. We can have some quantitative, this is qualitatively, but we can also have some quantitative estimation by computing with the correlation between the two fields. We can estimate this alpha coefficient, and we can also compare it to some analytical expression with some hypothesis like isotopic and homogeneous turbulence. There is an estimation linked to the helicity, the kinetic helicity. And this is what we computed. We computed to see if the electromotive force was well correlated towards the toroidal magnetic field for the alpha effect, or towards the resistivity, because we wanted to check the hypothesis. Is this alpha effect or is it non-diagonal resistivity? And we found that it's the alpha effect. So the electromotive force is correlated with the mean toroidal field.
How do you calculate the electromotive?
So this is come from the small scale, so the non-axis symmetric parts. The average here is the axis symmetric.
So an average on around
exactly. So I average the product of the small scale velocity, so U cross B for only the small scale.
How do you define the small scale versus the large scale?
That's, for me, it's axis symmetric versus non-axis symmetric. So and it's also we can, this is for the correlation, we can estimate the value of this alpha effect, and it matches really well with theory that comes from helicity. And also with this theory, we can also predict what's the period, what of the reversals, the dynamo period. And we find a very good agreement. So from the value of the alpha effect and the rotation profile, we find a very good agreement between the theoretical prediction and the simulation prediction, which means we can really see an alpha omega dynamo in the simulation, which generate the axis symmetric field. Since this was a new behavior that we didn't have in the incompressible model, we tried to understand why do we have this new behavior, and we found that it's an impact of the density gradient. So when we compare two different simulations, what with the density gradient, so the analytic model, and one without density gradient, you can see two differences. So one is the localization of turbulence. Because there is no high density region, the forcing is efficient in the full domain, and we have turbulence everywhere, while it's localized only on the lower density region. And you can also take a look at the butterfly diagram, which is much more chaotic when we don't have any density gradient, and while we obtain a clear butterfly diagram for the case with density gradient.
These butterfly diagrams are the functional latitude, so it's an average radially, or
no, it's given at a given radius. I just said, yeah. There is a radial structure as well, which is constant over some small scale, basically. But it's, yeah, it's at a given radius. One also differences in the equatorial plane, which could be an impact of buoyancy. This is why we look what happens if we compare without buoyancy and with buoyancy. And you can see the difference quite clearly. As without buoyancy, you have turbulence in the equatorial plane. While when you don't have buoyancy, you have turbulence in the equatorial plane. When you have buoyancy, you don't have any turbulence because it damps the radial movements. So the movement in the direction of the differential rotation. This is why it damps the MRI turbulence there. And you can see also the difference in the butterfly diagram, which without buoyancy is a lot more noisier in the equatorial plane, and otherwise have similar period and similar structure in the mid latitudes where the turbulence is the same. It's really the same alpha omega dynamo mechanism that stay with or without buoyancy. So we saw the impact of this different parameter, and we can compare for the dipole, for both with the incompressible results and all those new simulation. For that, we had to normalize the value of the magnetic field. So normalized by density, the angular velocity, and the length of the shell. And so we find that it's similar, even though the linear relationship is not exactly the same. It's still approximately similar for both anelastic models that are in blue here and the previous incompressible model here. There is stronger turbulence, as you can see, the total field is stronger for the models without density gradient and a similar dipole, but this could be due to the aspect ratio between previous incompressible, which was a lot thicker shell compared to the new models that were thinner. So it could be an impact of that. And yeah, we have a ratio which is comparable to some observation absorption line. So if we go back to compare for this dipole that we generate, we can do a summary between the incompressible and anelastic one. So this is the dipole intensity inside the simulation. Then we have to take into account that it will still cools down and compress. So this is why we take the radius and do a factor of compression with flux conservation, which amplified further the magnetic field. And if we also take a factor of the high PM, so when we have a lower resistivity regime that we found in local simulation, then we reach such final dipole intensity for both models, so 10 to the 15 for the incompressible one and 10 to the 14 Gauss for the anelastic one, which match well with Magnetars, and the anelastic dipole could match more to superluminous supernova because it's a bit weaker. It can do more late time energy injection, but it might not be strong enough to have jets forming in evolution. But there's still many uncertainties with this model. For example, the compression, how do we pass from 25 kilometers to like 10 kilometers, and how the differential rotation evolve in this time, how the thermodynamics evolve. And then maybe the field might be a bit weaker in the anelastic case due to the fact that we don't have any turbulence in the high density region. So that might be a numerical artifact there, but we should keep in mind. So to conclude, in the local model, we were able to explore the high magnetic Prandtl number regime and found that we have a plateau in the energy for a high magnetic Prandtl number. This local model has also comparable turbulent properties than global model. We find similar results. And for global model, in the incompressible model, we found that we are able to generate a subdominant dipole, but still quite strong, that can, as you saw before. And it's also mostly an equatorial dipole, a non-aligned dipole that is generated by the small scale. And when we add more physical ingredients like density and stratification, then we still obtain turbulence in a dipole field similar to the incompressible model, but we have a new behavior, a mean field dynamo with density gradients. And it really supports that the MRI is able to generate a strong dipole. And it opens also some perspective on the explosion because this alpha omega dynamo could be put into explosion simulation. So we could have like amplification inside and have the large scale explosion to see how does it impact this dynamo process. And there is still some studies to be done. What happens when we have interaction with the convective dynamo inside, and how does the two regions, the MRI and the convection, interacts. There could be some further analysis as well. The gravitation, since we have variation of density, there could be some gravitational wave signal that could be studied. Also, to compare more precisely to observation, we need to relax and do some long-term evolution, like Clara and Daniele wants to do and done of the magnetic field. And this instability is also very important to study for neutron star measure. And thank you for your attention.
Thank you a lot. I think it was very comprehensive, very clear. Thanks a lot. Questions? I think there are many. Nadia?
Okay, thanks. Very nice overview and very nice results. Can I ask you a question on your previous slide on the comparison between the previous one, compressible and elastic?
Yes.
One of them.
Sorry.
This one. So you said that, I mean, in your final
Yep.
lines below, you said that then it's more probable that superluminous supernovae actually comes from the inelastic effect rather than the incompressible one, right? This is what
Yeah. Yeah, this is
But
because it's
but if I look at your table, actually the inelastic one have, to me, it's way more efficient to increase the dipole effect because you have orders of magnitude in there when you have one. So can we reliably say on the basis of that actually the fact that you reach lower values of the dipole in this scenario, it's mainly due to the assumption of your simulation in this case? Or is it indeed more effective?
I think that's, I think it's the artifact of my simulation, because since it's a larger scale, like 40 kilometers, this is why it increases higher because you have higher compression. But that's one uncertainty. We don't know for sure that we can assume flux conservation in this evolution, and how the turbulence evolve for the MRI while compressing. That's, for me, something unknown. This is why it may appear as a stronger amplification, but actually it might not be the case. So,
So you wouldn't say reliably that from your simulation, the inelastic scenario is more effective in amplifying the dipole rather than compressible?
No, yeah, exactly. Because it's mainly, this is why I would compare with when you normalize by density between the two models, you in the end obtain similar results. But it's true that the magnetic field seems a bit stronger for the inelastic case.
Okay.
Thank you for very nice results. Very nice talk. Many questions, maybe we'll ask afterward. A couple of questions. So you showed a quite impressive agreement between neutron theory and in terms of periodicity. Do you have numerical convergence in that?
Yes, because we don't have numerical dissipation. It's a pseudo-spherical. The numerical dissipation is very low, so when we increase the resolution, it doesn't change the results.
You always have numerical dissipation, but anyway, so you tested with the resolution change.
Yes, and similar results.
And about the MRI part, I didn't, maybe I missed it. How many orders of magnitude are you able to amplify the field?
So in my simulation, not that much, because if you look at the magnetic, here, the initial magnetic field, it's a few times 10 to the 14, and when you look at the final one, it's a factor of 2 amplification. But this is because we cannot go towards lower because of resolution issues. And this is why we start only from a small scale. The idea is the amplification from weaker magnetic field would happen as what we see in local sharing boxes, where we can resolve the MRI for weaker magnetic field. That's something we cannot do in a global spherical model. And so this is why we wanted to make the transition from this local boxes amplification towards the global magnetic dipole.
So you basically assume that you first have a kind of small scale dynamo that amplifies the field only on a small scale.
Exactly.
This in the large scale simulation.
Exactly.
And then produce the large scale component.
Exactly.
Okay. Okay, I didn't understand that.
Okay. There was Clara?
Yes, so for the equation of state, you use the equation of state coming from nuclear physics or just?
So yeah, it's from the 1D simulation that we take from the Garching group, and I think it's LS 220.
And So in proto-neutron star equation of state, they should, like, the temperature is not zero, so it's not very realistic to use equation of state at zero temperature. Do you use a fixed entropy or fixed temperature?
For my case, no, I just take the entropy profile that they
Okay.
obtain in the 1D simulation and put it inside my simulation.
Okay. So you use fixed entropy.
Yeah, I mean, you can have some perturbation of entropy. It's not totally fixed, but the background is fixed.
But you implemented the equation of state in the magic simulation?
So it's not inside because the thermodynamical background is it's included inside the equation of state.
Okay, right, yeah.
But there's no
The background is taken from
exactly.
a simulation, including that equation of state, but
But then you don't need an equation to solve the anelastic equation.
okay,
You
but
don't need an equation of state.
Determine, like, the mass. And here's another question. You mentioned about the tilted angle that's mostly equatorial, and you said that you might need to do different boundary condition, different initial condition to see if it would always be equatorial.
Yeah, we tried and it was it's changing a bit. It's a bit stochastic, but it was dominating by the equatorial component.
other questions? Stefan?
I have a curiosity. When you talk, in the beginning, you mentioned the fact that you can create Magnetars from segment. Since the condition of the inertia is very different from one different I wonder, in your opinion, we can expect a radically different topology for this kind of
So I've done some simulation, like similar anelastic model for dynamic transfer measure, and the results are quite similar in terms of topology. And same, it still creates a dipole, which is a few percent of the magnetic field strength.
This factor that you find in the simulation, this equatorial axis, the component, I think is very interesting in terms of gravitational variation for the axis. Also, if you have this component that is strongly misaligned with the gravitational axis, you can increase the information that can be associated with.
Yeah, I don't know if the magnetic field would be strong enough to, like, the deformation would be strong enough as well. That's something.
That's the part principle that goes in that direction.
Just a question on a similar point. So this distribution that you find, how is actually related to your initial assumption on the angle between rotation and magnetic field? So if you misalign this will be different levels.
No, because there's no dipole initially, because there's no misalignment. Like there's only the small scale. I'm not sure.
Okay. Okay, so this is only the small scale one.
Yeah.
Okay, there any other question? No, in Zoom, the chat is empty, so, okay, you can, thanks Alexis
Thank you very
again.
Thanks a lot.